Okay, so yeah, so last time, just go through this one more time. So we said if Z is standard normal, so deriving the chi-squared density and studying it, then Z squared is chi-squared 1, but that's equal to, do you remember?
Is that gamma 1/1/2, 1/2?
Yep, gamma 1/2, right? So if you remember the gamma, you get the chi-squared for free. Also, if you have Zi or Z1 to Zn IID standard normal, then the sum, because gammas, we showed independent gammas with the same rate add, then the sum of these squared is gamma. Well, they add, right? I just have n of them. This term adds. This must be the same. It is the same. So this is just gamma n over 2 1/2. But this is equal to a chi-squared with n degrees of freedom then. That's defined to be that. Okay. All right. So we know then that because we know the PDF for the gamma, we can quickly write down the PDF for the chi-squared. So just to remember, this just reviews. So for example, PDF for, let's just do something like chi-squared with, say, 40 degrees of freedom. What do? We write the we know the gamma, right? So this is the same as gamma 21/2, right? 21/2. If you remember everything, it's f of x equals 20 down here. This is 19 factorial, right? Because it's integer. And up top, we have lambda x to the alpha minus 1, so to the 19th power, and then lambda e to the minus lambda x, e to the minus x over 2. Of course, this is only for positive. If you want, you can include 0. Makes sense there. Right, so that's it. Or if you want to just write the nice form, right, with just a constant taking all the constants out front as a k, it's very nice. It's very short, right? You just have k x to the 19th power e to the minus x over 2. That's it. And 0 else, okay? And it's understood that that k has to be chosen, so the integral is 1. So that's you see, you just they're the same thing. So that is, so the integral, in other words, the integral of x to the 19th e to the minus x squared is 1 over k, where k is the product of all those things up there in this expression up here. Okay, is that all right? So review from last time. Yes, that doesn't look too bad, right? And remember, this has this form. If alpha is bigger than 1, it's concave up, concave down, concave up. Goes on forever. The mode is at 19 over 2 because of the lambda. So, and the mean would be at 20 over 2. Let's see, it doesn't make sense to me. Hold on. The mean would be at, 19 over 1/2, right? So this would be at 38, the mode, and the mean is at 40. I know because the expected value of z squared, a standard normal squared, is 1. Do you know why? Let's have, like, for extra unplanned discussion, we'll go to a different color. So how could you show the expected value of z squared is 1? So can you think of a way? A quick way. We could always do the integral, but we probably don't want to do that. So ez squared is just by just using that short form for the variance, I could write the variance of z plus the expected value of z all squared, right? Do you see this? Because if I subtract that last thing from both sides, I get the expression for variance. And standard normal has a variance of 1 and an expected value of 0. So it's 1. So when I was doing this and I accidentally said 19 here, and then I changed it to half of 19, I went the wrong way, right? It's 19 divided by lambda, which is a half. So it's 19 times 2. That looks much better to me. This is the expected value. This is the mode. And it looks like this, okay? Just to give you a feel for it, because you want to know, okay, it doesn't have much chance to be down here. It doesn't have much chance to be up here. It gives you a certain sense for what these things are. And we'll never mention it again, okay? All right. Is that a deal? All right, okay. So next thing. Remember, if you have to go, I'm just kidding. Okay, next thing. It turns out if I add two normals, I get a normal, and I don't even need the variances or the means to be the same. So this is a real big one here. If I have two independent, so let's say fact, let x be, say, normal mu x sigma x squared, y normal mu y sigma y squared, independent, then they have to be independent. Then sometimes you could say uncorrelated, because in the normal case it's the same thing, but independent. Then x plus y, does anybody know? X plus y is again normal. And what do you think happens to the mean?
It's gonna add up.
Yeah, they add up. I put you back on the camera. Okay, yeah, they add up. So we get mu x plus mu y, sort of makes sense, right? Adding them together. Sigma x squared plus sigma y squared. But you wouldn't know this ahead of time. You have to show it. And we can show it with that convolution method. It's a little ugly. I thought of doing it for a simple case, numeric case, to show you. And I'm sort of thinking I'm not going to do it. We'll see if there's time at the end of the lecture. I'll show you for a simple case. Like we'll add two standard normals and see that we get something that's normal with mean 0 and variance 2, something like that. I can do it. It'll take some time, and I don't want to get bogged down in that detail right now, but that's how you do it with that result we had. Okay, also follows from this, and what do you think? If, say, x I normal mu I sigma I squared independent, then the sum, we just add them up. So nice, right? You couldn't really have hoped for anything better than this. Yes, okay. Let's, instead of doing the proof for the, the check, we'll do an example first, and maybe we'll do it at the end, or we'll do it actually in class or something like that. We'll see how it goes. All right. So let's do an example instead. You'll see, you're gonna like it. It's not hard. Suppose we let xi I equal 1 to 3 be the number of customers in in three chains, three branches of a chain of stores, Big Y or something, Market Basket 32, whatever you want. So let x1, x2, x3 represent those things, and we'll say normal 350 squared, normal 250, 50 squared, normal 350, 70 squared. This is the big one, the big Y. Okay, let's find probability. The big one has more customers than the other two put together. So, right, you see, is possible. Does anybody want to, what to do?
360,
Add them up, add them the first two, and then do the normal.
The x2 and the x1, right, are normal again. Yep. And then I can subtract from x3. Is that okay too? Well, if you like, you could call it adding, and we could just change the, like, we know that any constant multiple times the normal, we know that distribution too. So I can call it adding minus x1 plus x2. And so I get one thing on the one side and I own it greater than 0. Okay, so that's what I'm going to do now. Can I leave you on the camera? No?
Well, I don't mind either way.
All right, if you object, just speak up. It's okay, it's too late. I've already put you on there, so it's all right.
Yeah, that's fine.
It's more festive. I like it better to see you, but maybe I'll get fickle and turn you off in a little while. Okay, so this is equal to. All right, so find this. So this is equal to. So this is equal to. This is the probability that, say, x3. Can we just subtract them all right now? Minus x2 minus x1 is greater than 0. All right. All right. Or equal to, say, the probability, say x3, just to make it super clear, plus minus x1 plus x2 is greater than 0. I don't want to be silly, but I want to make sure this all follows from that stuff. All right, and now, what's the distribution of x1 plus x2? Can you see? Yep. So go ahead. We'll write it right here. x1 plus x2 has what kind of distribution? Normal. What's the mean? Maybe you don't know if I mean the minus sign or not. Well, anyway, x1 plus x2 is, we just add the means, right? So I get 550. So let me apply the minus sign. So minus 550. And the variance is, okay, yeah, I understand. So it's harder with these squared things. You got to first square them and just, maybe they're not perfect squares. So we get 2,500 plus 2,500. So I get 5,000. Now that is not negated, right? Because it's a squared times the variance. And I just get the same variance as if the minus sign wasn't there. So 5,000. So that's this whole piece. Okay, and then I want to add that to this piece, which is normal. You can see 350, 4,900. So this is equal to the probability that, let's say, minus 200 9,900 is greater than 0. Sorry, I'm getting too excited. Okay, so we need to make it standard normal, right? So I'll just write it like just like this, Z. No, don't call it Z, call it what else? W or something. W normal minus 200, 9,900 is greater than 0. And now I'll make it Z. I'm going to add 200 to each side and divide by the square root of 9,900. So this is the probability that Z normal 0, 1 is greater than 200 over the square root of 9,900. I can take out at least a 10 on the top and the bottom. So I'd get 20 over square root of 99. And that is just slightly bigger than 2, right? Square root of 99 is a little less than 10. So it's the probability of standard normals a little bigger than 2. And I get, 2.01 or something like that. So 1 minus P norm of this number. I think this is what it was, or I can't tell if it really is what it was, or I just wrote that down as I was estimating it in my head. But anyway, you get the idea, right? If they're independent, the parameters add. It's nice, right? It's a pretty complicated step here from where we were doing just using one normal. Now we're able to combine them and solve many more problems without really anything very hard. You just get this, and it's from the fact that if you add normals, you get another normal and the parameters add, which I'm not showing you. And to show you in the general form would take a while. It's a lot of algebra and manipulating the integral. I was just going to do a simple demonstration of it, but even that would take some time. So I think we're going to not do that, at least not yet. I'll see if everybody really begs me to do it. I'll do it toward the end, okay? Do you want to go off camera? Everybody good? Okay. Dylan, you all right? Okay. All right, so let's do one more then. B, find the probability that, say, x1 plus x2 plus x3. So this would be something you'd want to know, right? Do we get an aggregate number of customers over a certain threshold? I'm just double counting the ones in store 1 for some dumb reason. I don't know why. No, it's because it's a math problem, not a real thing, but maybe, I don't know. Maybe that's the one where they stealing from store 1 or something, so they want to know. I don't know. Anyway, okay, let's just do this. So this is equal to, what are the parameters of the first one? Oh, we need to see it again. So 350 squared. So what's 2x1? Let's just write 2x1 here. What's the new mean?
$900.
2x1, x1 is 300, right?
Oh, yep.
Yep, so 600. And the new variance?
Oh yes, we are doubling it. Never mind. Thank you.
Yeah, no, it's okay. So the variance though, what are we multiplying that by? So it's 2,500, but if I take 2 times the x1, that has a variance of, anybody remember? Here, I'll turn you off so that I'll punish you for no, I'm kidding. No, I don't. So maybe it's more relaxing. So 2,500 times 4, right? A squared times sigma squared. So I get 2,500 times 4. So that's 10,000. That is a perfect square. Yeah. All right. So what do we have? We have the probability that a normal. Now let's add them all up. 600, and here I have another 600 here. I can mess this up now. So the mean is 1,200 and the variance is 10,000, 2,500, 4,900. So normal. I forgot, 1,200. 20, so 69, 74. So 17,400 is the new, I think. Variance. So I want the probability this is greater than 1,100. So make it standard normal. So that's the probability. Standard normal 0, 1 is greater than minus 100 over the square root of this. So 10 root 174 minus 10 over root 174. That's about 13, right? Or 14. It's between 13 and 14. So actually I did it here. This is minus 0.758. And this better be 1 minus P norm, right? 1 minus P norm minus 0.758. So in other words, I got something like this, standard normal, and it's this area, right? It's the area greater than minus 0.75 here. So from symmetry, I could also, there's a simpler way to write this. Can you think of it with a positive, with just P norm? What would you put in for the argument?
.758.
Yep. So it's a good thing to do. It's fine. It's a little shorter, nicer to read. But yeah, either way. So and what is it? Well, you get the idea. It's more than a half. This is actually 0.78 or something like that. All right. All right, I got a discrete example to do for sums of independent random variables, and then we're going on to conditional distributions, conditional densities. So one more example of these. So the next thing, item 5. New thing already. We'll get back to the adding independent normals. It's going to be important in the next thing, multivariate normals. But for now, that's it. Okay, next thing, adding discrete RVs independent. Okay, this is also a type of convolution. But it of course is different. There's no integral. So we're just gonna, this is a nice fact too, so we're gonna write this down. Suppose X is Poisson, lambda 1, Y Poisson, lambda 2, independent. Then X plus Y Very nice. I think when you do this, it just really hit me that, you see these, like, I add 2 gammas, I get a gamma. I add 2 normals, I get a normal. I add 2 Poissons, I get a Poisson. You get spoiled, or you start thinking like everything's like this. It's actually very rare. And these maybe these are why these are so useful and things like this, but anyway, does it make sense intuitively? Remember what X and Y represent? Don't they represent counts of events like customers in the store in a certain amount of time. So, if X keeps track of the customers in, store 1 and Y in store 2, and I add them together, I get something, same distribution, and the rates just add. Sort of makes sense. At least the part about the rates adding should sort of make sense. Okay, so to derive this, so we'll show this now. So indeed, what do we have? Probability X plus Y equals N. Here's the moment where you see it looks like a convolution. There's N plus 1 ways this can happen, right? K equals 0 to N. And we're going to add up these ways, right? So the probability X equals N or K, and Y equals N minus K. I want to add up these, right? Because each one is mutually exclusive, and each one is a way to get N, N for X plus Y to equal N. Okay, and you can't go past N or below 0 because you can't have a negative number for these things. All right, so this should make sense. Now, this is mutually exclusive, so you could write ME there. The next thing is to write this, K equals 0 to N, and we can break them up like this. Why can we break these up as a product?
Independent?
Independent, they're independent. So this is what you get. You get this nice feature. And this we know because they're Poissons. So let's go ahead and put in their PMFs. So the first one would be e to the minus lambda 1 to the k over k factorial, e to the minus lambda 2 to the n minus k over n minus k factorial. Yes. Okay, very good. See some good things happening here. You notice you get this k factorial n minus k factorial. That looks like the n choose k, right, in the denominator. So why don't I multiply by n factorial over n factorial? And I can write it like this then. E to the minus lambda 1 plus lambda 2. I'm taking that constant term outside the sum, and I'm going to write 1 over n factorial out here. And then inside, I have k equals 0 to n. And now combining the n factorial in the numerator with these two, I get n choose k. And what's left? The lambda 1 to the k, the lambda 2 to the n minus k. All right, so that's right, that's what I want. So that's exactly what I want. Lambda 1 to the k, lambda 2 to the n minus k. And what is this? Remember? Back from the first class? Second class, maybe? Binomial theorem? This is just lambda 1 plus lambda 2 to the n. That's all it is, right? Binomial theorem, and you're done, right? That's your proof. See? That's the probability that a Poisson random variable is equal to n. It shows, since it is that, and that's the probability we computed based on only the information we have just shown that x plus y is Poisson with that rate. All right. Ready to keep going? do you want to pause the recording? Let me pause the recording. Okay, so next section is conditional, called conditional densities or distributions. And it concerns wanting to solve for a conditional probability when you have continuous random variables, or as well conditional expected values. So you'll see. So we need a definition. So definition, let X and Y be jointly continuous RVs with PDF f x y. Then we define the conditional probability of X given Y as follows: f of X given Y, those are capital letters, these are lowercase letters. X given Y, we never put a little bar inside the parentheses of function as of now, but now we're going to do that to mean the following. This is a definition, so this equals f x y over f y, the marginal distribution of y. So this is called the conditional density or PDF of X given. All right. So some things follow from this. We'll see. We'll look at this in a minute a little more closely. So we have some things follow. If we want, say, the probability X is in some set A, given Y equals some little number Y, some fixed number Y, then this is just equal to the integral over A of this conditional density, X given Y, little x given little y dx. And if I want the expected value of X given Y equals some number little y, well, that's just equal to integral over all X f X given Y, little x given little y dx. Okay, I just use the conditional distribution. It restricts the conditional density. It restricts the density to where y takes on that known value, basically. So we'll see this. Let's do an example first. So example, suppose we have joint X and Y are jointly continuous, fxy equals, say, k, say, x squared, x plus y, 0 less than x. So not less than y less than 2, but just x and y both between 0 and 2. So a square in the xy plane, and then 0 outside of that.
Is that a K in front? Sorry, I missed.
It is a K, yeah, it is a K, and I was worried I didn't want a K, but I think K's okay. Now let me call it a C. You know, it's funny that you mentioned that, because I was looking at it, I was saying I think I want to call that something C. Yeah, let's just call it C. It's a constant, like I don't want to bother doing it. We could of course do it, right? Take the double integral over 0,202 and find C. But let's just leave it C for now. Actually, I wonder, I'd have to reshare the screen. It's not worth it. Maybe at the end of this, we'll look at this. I did a 3D plot of this function. It's not very revealing. you can see it's going to be increasing as X and Y get bigger toward 2, right? Especially in the X direction. And it's positive everywhere, which is good, right? It's a density. All right. So it's a real density, and it doesn't really matter what it looks like. And it's kind of hard to tell anyway from the 3D plot. So, all right. So A, let's find the probability that X is less than 1, given Y equals 1. One thing that's interesting about this, when we talked about in like chapter 3, when we talked about conditional probabilities, we always said that the thing given had to be non-zero because we're dividing by it, right? We're always taking, like, say, the probability of A given B is probability of AB divided by the probability of B. So the probability of B couldn't be 0 or it wouldn't make sense. But that was for discrete, and this is different. Here we have a density, so it is different. In other words, the event that Y equals 1 does have probability 0, but it's still okay because you're integrating. Okay, everybody all right? I just want to find this. I'm just going to do it, as I said, in this first one up here. So let's just do it, just problem it out. Okay, f, x, y, here I put little x, here I can put little 1. I don't need a whole formula for it, right? It's just asking for me at that one point. If you needed it for other points, or you needed to sketch it as a function of y, you could do that too, but let's not. We just want this probability. So this equals the joint f x1 divided by f y of 1. And this we can just call, if you think about it, fy of 1, the marginal density of y at 1 is just, again, a constant. Do you agree? It's just a density in one dimension, and I'm plugging in 1. So it's just a number. So I can call that whole thing k. That's why I wanted to save the k for this. K x squared x plus 1 now. And this would be for 0 less than x less than 2, and else okay. All right. And now we just integrate over the region, right? So probability x less than 1 given y equals 1 is equal to the integral 0 to 1. We're going to have a k in the answer. We're going to have to figure this out. Let's just keep going though. Okay, getting there. This is equal to k times x cubed, so 1/4, and x squared, so plus 1/3, 7/12, 7k over 12. I need to find k, don't I? We need k. Let's get it from here, though. We could get it from back there, but this looks easier to me. So we need k. And so we have 1 over k is equal to integral 0 to 2 x cubed plus x squared dx equals 0 to 2. Let's equals, we can just do this, right? X to the 4th over 4. So I get 4 plus x cubed over 3. I get 8/3. I get 20 over 3. So k is 3/20. So probability x less than 1 given y equals 1 is equal to 3 over 20 times 7/12 equals 7/80. All right, well, I knew the probability would be much higher that x is greater than 1 than less than 1. So that part makes sense to me, actually. It's about 1/10. Even though it's half of the x's domain, its probability increases. It's very flat when you get for small numbers, right? So it's very low density on small numbers. And so it has a, so that's why it's more probability to be bigger. Any questions?
And can you remind us why it's between 0 and 2? The x is between 0 and 2.
Yeah, that's how it was defined.
Yeah.
Like this is how the joint density is defined. That x, this comma
Oh,
just means they
Wait, so a comma is just like, so they are in parentheses then? Sort
no,
of?
yeah, it's not really in parentheses. It's just it's like a short way to write. It's a short way to write this. Right?
Oh, I see.
Yeah.
Yep, I get it.
This is better if you just have time, you're typing it or something, but yeah. Right. All right, so let's do an expected value now. I think this is actually pretty interesting. You can think like, okay, I got this continuous function and it's going to be some 3D surface when I look at the density value versus x and y's value. But if I take a slice along a certain value, like say, I mean, really along anything, but along any line, but say along like some value for one of the variables, what's the expected value of the other? So you kind of go from a surface to a 2D curve. I don't know if I can draw this, but let's see, like if I have some surface like this, I know all those geometry guys can do all this stuff really well, but I have some surface like this, and what I'm doing is like at some x here, I'm just taking a curve. So, and now think of that projected into 2 dimensions, like I have something like that maybe. And I think the way I drew it is not really correct. I think this is going up actually like that. So I think it's actually like that. But you have, like if I fix x, right, and I take the slice of the surface, I get now what looks like a 1-dimensional density. The only thing is, it's not going to integrate to 1 yet. And that's really the reason you divide by the marginal density, is to make it integrate to 1. But you don't have to fret too much about that. We're going to look at that a little more next time. Yeah. So this picture is really very much a shameful picture, but maybe I can try again. Like, let's see if so I'm thinking the surface looks more like this and like this. So it's something kind of going up like this. And then if I fix x here along this line that's parallel with the y-axis, and I project down or project up from that line onto the surface, or I take the slice of the surface that is that has this x coordinate at every point and whatever y coordinates on the surface, and whatever y coordinates along here, and whatever densities along here, I take this line that is on the surface. That is like a density. The only thing is it's not this area, which is now vertical and perpendicular to the plane of xy, is not probably not 1. So you normalize it to make it 1. You divide by the marginal density. All right, it's enough of that. Sorry about that. I wish I could draw better. My cousin was an excellent graphic artist, but she's no longer with us, so. Okay, let's do an expected value. So the question would be like, if X is fixed, what's the expected value of Y? And you have this like, sort of this measure of how likely Y is to be along this X. Okay, so B, find, what do we want to do? E, let's do E of Y. So I'm flipping it, okay? Before I was conditioning on Y, now I'm conditioning on X, just to give us more practice with this. Hey, if we run out of time, we don't get to the T distribution, it's okay, we'll do that next time. We have enough time, I figured out. So, so what do we do here? It's just like before. So you can consider this a definition since it is new, but just take that to be what we talked about on this page, a couple pages back. You take this part to be part of this big definition. This is how you do probability. This is how you do expected values. You use the conditional densities. All right. So what do you think? Let's try it together. So E, Y, given X equals 1 is equal to, I need to integrate over all of X. I mean, I could write 0 to 2 right now, since I know really that's the right range. I can always write this because the conditional density will be 0 elsewhere. So let's just do this first as like a reminder of the definition. So it's going to be f of Y given X, little y, little 1, d, y, right? This should be y. I wrote the wrong thing. All right. Makes sense? Along this, so this here is this density, but normalized so that it integrates to 1. You can see that, right? Because what is this now? This is just f, y. Oh, y doesn't go first. No, it does go first there, but now I got to write it the right way. Now, if I'm going to write it in terms of its definition, which I was trying to do, this is going to be f, X is 1, Y is a variable still, over the marginal density fx of 1. Okay, so that's what that is. So that's really what I need, right? So let's go ahead and get that from the definition. So this I can call K again. I think we should do that trick again. So let's just find F. What's F1? Y. This is equal to, where the hell is it? This is equal to C or K or something. C? Yeah. C. X is 1 now. So that's good. That makes this pretty simple, right? C, Y plus 1. Right? Yeah. X is 1, so X squared is 1, and X is 1. So this is what I get, and this is for 0 less than Y less than 2, and 0 else. Let's find, oh, no, let's not find that yet. Okay, so now we have, what does f y given x, little y given 1 equal? This must equal this divided by some other constant. So I'm going to bring them all together into a single constant. So this is just equal to k, y plus 1, 0, 0. All right. Okay, so let's find k. Let's find k first this time. So to find k, we know that k, 1 over k must equal 0 to 2 y plus 1 dy. And this is just equal to y squared over 2 plus y. Four. K equals 1/4. Okay, so K equals 1/4. So let's answer our problem now, finally. So E y given x equals 1 equals integral 0 to 2 y times fy given x, y given 1. So that's 4 times y plus 1 dy. Look at that, just a regular expected value thing now. This is equal to 4, 0 to 2, y squared plus y dy. 4 times y cubed over 3, so 8/3, y squared over 2, so 2. 6/3, 2. 14/3, so oh, K, sorry, K is a quarter, right? K is a quarter. I got too cute. Hold on. I knew it didn't make sense, right? Hey, this was planned to make sure that you understood that these things have to make sense. I did this on purpose to make sure that you would see that what can happen, that you got to check and make sure things make sense, right? The expected value of x must be between 0 and 2. So it would have made absolutely no sense at all. And I was tipped off like a secret agent. So I have 1/4. What is this in here? 14, let's see, 6/3, so 14/3, 14/12, 7/6. There we go. That's a really nice expected value for y, don't you think? And remember, y wasn't, like, I think x's will be more closer to 2. Y is getting bigger, but not that much bigger from 1 to 2. Remember the definition up here. X is being cubed, and y is linear. So, yeah. So it's increasing. I do expect it to be between 1 and 2, and it's 7/6. All right. Any questions? Okay, so let's go a little more just to introduce the t-distribution, and then next time we will, so just so you can get it marinating around in your brain a little, and then we'll get into a little bit more of the gore in the next class. I think this is good so far. I probably should stop it right here because the lectures are better when the recorded lectures are shorter. But let me just first of all just define the t-distribution though, and then we'll stop without sort of deriving the PDF. That's what we'll want to do next time. By the way, let me just fix this. This should be 1/4 to. All right, so the t-distribution, it's really important in statistics. A lot of models have parameters or other things that are t-distributed, and you'll see in the next course, if you're sticking around for that, that it's an important distribution. So okay, so how do we define it? So we're not going to get into the PDF, but we're going to give the general idea, and then talk about when it looks normal and not. Okay, so we take let y be, basically this can be the definition, although you can wait for the PDF as well. So let y be chi-squared n, so that means gamma n over 2, n over 2, n over 2, 1 over 2 as well, and z standard normal, and let these be independent. Okay, and then set t equal to z divided by the square root of y divided by n. Okay, this is called t random variable with n degrees of freedom. And we want to find the PDF of t. And basically in this course, just because this is the right time to do it, you will never do it again, probably, but it's never really shown to you. And it's not a complicated PDF, so it's kind of weird that it's not really shown unless you kind of pursue the math statistics. And the other thing is that it's important to sort of have a feel for it too. So this helps with that. And it's a really nice way to sort of look at conditional densities. So we're going to derive the PDF using conditional densities, but not today. I'm not going to do that today. Instead, let's just look at one thing. There is this result that if n gets big, right? If n gets big and y, right, is just the sum of n independent standard normal squared, then what should this approach say in the limit as n goes to infinity?
Sigma squared.
Right. So if you're thinking central limit theorem, which is a good way to think about it, you can think of the z squared, the z1 squared, z2 squared. You're thinking of the variance of that divided by n is the variance of this whole object inside here. And well, the variance of that is finite. We can show that. I mean, the other way to think about it is, since it's well, it does obey. Yeah, maybe I should just abandon this. I am feeling a little bit out of time. But the thing is, if I think of each of this as the sum of each of independent things, like z1 squared plus zn squared, and I am taking the average over n, then I get sort of like an average, right? I get a sample mean of these. And you've seen usually that, like, as long as the variance of this is finite, then this will approach its mean, right? You can use the weak law of large numbers. You can use Chebyshev to say the probability that this is greater than epsilon. So the probability this minus, what is the mean here of the z1 to zn squared, just of the z1 squared, say. We just saw it before, it's 1, right? So the probability that this is more than epsilon away from its mean is what? What does Chebyshev have to say about this? It's less
than epsilon squared over sigma squared.
Yeah, right. It's less than or equal to epsilon squared. I'm sorry, epsilon squared is in the bottom, right? The variance of this whole thing.
Oh, yep.
The variance of this whole thing, which is 1 over n, right? Oh, no, I need the variance of z1 squared. Yeah, that's the thing. And I haven't shown what that is yet, but it's the variance of z1 squared. So we'll do this next time. It's not that hard. Variance of z1 squared over n, okay, over epsilon squared. Okay, but if n's really big and the variance is finite, this goes to 0. It doesn't matter how small this is, it still goes to 0. That goes to 0. So this goes to 1. So if it goes to 1, and if I can think of t goes to then z over 1, you can see it's equal to z, standard normal. It's true that as the degrees of freedom increase, t approaches the standard normal. And right from the beginning, when we see the PDF next time, you'll be able to see that it looks fairly normal already, even for, like 8, 7 degrees of freedom. Okay, this is kind of sloppy. I'm just sort of wanted to get it marinating in your brain, but this is where we'll start next time. I'll do it carefully, and we'll go on to actually find the whole PDF. Mainly, I want you to know it in K form, like a constant times some function. The function's very easy. The constant's very ugly. At least you'll think that at first. And then that's good. Okay, and then we'll move on from there. Just a little more to go, and that's it. I'm going to stop the lecture now, the recording, and just stick on for a minute if you want. We can talk.